Hi guys, it's Mrs. Jackson. This video introduces the concept or the skill of predicting products for double replacement and single replacement reactions. So as we get started on this, a couple of things you're going to need to have out are going to be your periodic table. You're going to need your notebook for taking notes, your pencil, and your thinking caps. So let's go ahead and get started. The first one we're going to look at are double replacement reactions. Now remember, these are the ones that have two ionic compounds. So when we're looking at these, there are two ionic compounds. You've got sodium chloride and you've got, pardon me, silver nitrate in this particular example. And so we've looked at these in the past. I've got a metal and a non-metal combination, a metal and a non-metal combination. So what we're going to do when we are predicting products for these chemical reactions is we do something I call the split and switch. So what we're going to do is we're going to practice dividing these compounds into their ions. So the sodium plus, chloride minus, silver plus, and then the nitrate is NO3 with a minus charge. And all they're going to do is trade partners. Okay, so you want to think of this almost like foil in math class. The outsides are going to go together. So you can see that the sodium is now going to partner with the nitrate and the silver is going to partner with the chloride. So you're going to connect your outsides to the insides, and then you're going to rewrite the formulas based on their charges. So if sodium is a +1, chloride is a -1, silver is a +1, nitrate is a -1. When I bond silver or sodium with nitrate, it's a +1 and -1. I get NaNO3. When I partner the silver, the +1 with the -1 chloride, I get AgCl. It's always going to have the positive ion listed in the front. So there's your positive sodium, here's your positive silver. And then the negative ion is always listed at the end, NO3 for nitrate and Cl for chloride. So let's do a couple of examples to see how this works. So for our first example, you can see that I have aluminum chloride and I've got sodium sulfate. And I've gone ahead and I have circled sulfate for you because I want you to remember that this acts like one big particle. Okay, it is not going to break apart. But the rest of these atoms are going to split apart in solution. And when they split apart, they're going to find new ionic partners. So this is why I call it split and switch. All right, so we have to remember that the aluminum and the chlorine are all going to break apart, and that the sodium is going to break apart from the sulfate. So I'm going to split and switch. And for this, I'm going to get two products. All right, I'm going to have two new ionic products. And remember that the outsides are going to partner together and the insides are going to partner together. So my outside aluminum and sulfate are going to partner, and my inside sodium and chlorine are going to partner together. So the first thing that we want to do is we want to identify what the charges are for all of our ions in solution. When I look up aluminum on my ion table, it's on the back of your periodic table, aluminum is a +3 and chlorine is always a -1. Now those break apart, and I just want the one chlorine with its charge. We're going to predict our products on the other side, and then we can worry about balancing. Sodium sulfate, when it comes apart, you're going to get sodium atoms or ions, and they're going to have a +1 charge. And remember, I have circled this sulfate because it's all going to stay together. So the next thing that I want to do is I want to write my formula for sulfate, SO4, but it has a 2- charge, and that's going to be the charge for sulfate. So on the product side, remember that my outsides are going to bond together. So my aluminum is now going to bond with my sulfate. So over here underneath my blank, I'm going to write my charged particles, Al3+ and SO4 2-. and those are going to go through the split and switch. I'm sorry, those are going to go through crisscross reduce. So I'm going to bring the 2 down here, and I'm going to bring the 3 outside of parentheses. So the first thing I want to do is I'm going to have to put parentheses around sulfate. And then what I'm going to do is I'm going to cross my charges down. This is the same thing we practiced for weeks and weeks. The 2 comes down here, and the 3 comes down here. So my new product in the blank is going to be Al2 parentheses SO4 parentheses and with a 3 outside. So we crisscross those and then we reduce them. Underneath the other blank, I'm going to partner my other 2 ions. I'm always going to start with a positive, so I'm going to start with sodium, and it's going to bond with chlorine. So now my insides are going to partner together. So I've got Na with a +1 charge, and I have Cl with a -1 charge. Remember, you're looking those up on your periodic table with the ions. And then I'm going to do what we've done before. I'm going to crisscross reduce. So I bring a 1 down and a 1 down, and the final answer in my blank will be NaCl. And then I have balanced all of my formulas, and the formulas have to be written first, and you'll notice that I wasn't worried about any of the subscripts on the left-hand side. I worried about the charges only. Once you have your formulas written and you've got Al2, SO43, and NaCl, then you can go back and you can balance these by putting coefficients in the front. So I would balance this by putting a 2 in front here. I would put a 6 in front here, and I would need a 3 in front here. So the balanced ratio on this one would be 2 to 3 to 1 to 6. And that's how you would predict the products and then ultimately balance it at the end. Okay. Let's do a second example down here at the bottom. Same principle. I'm going to split and switch, and so I come to the magnesium hydroxide and I break it apart. And I do the same thing for sodium and sulfate. And then I want to write down below what my charges are when these break apart. Now again, when I look at my ions, I see I've got hydroxide here, and it's going to act as its own thing. And I have sulfate on this one, and it is also a polyatomic ion, and it's going to stay together. Hydroxide will stay intact, and the sulfate will stay intact. So down below, I'm going to write the ions that I have. I'm going to have magnesium, and when I look it up, it is a 2+ charge. And I have hydroxide, which is OH, with a -1 charge. In my second formula, this is sulfuric acid, I wind up with hydrogen ions, and I wind up with sulfate ions, SO4, 2-. So on the right-hand side, for double replacement, I'm always going to have 2 products. And just as before, my outsides are going to repartner. So my magnesium is going to partner with my sulfate. So over here under the first blank, I'm going to put Mg with a 2+, and my SO4 with a 2-. When I crisscross reduce and I bring the 2's down, I start off with Mg2 SO42, but I can reduce those 2's to 1's, just like we practiced when we did our chemical formulas. So I'm going to make those 1's, and the final answer will be Mg SO4 in the first blank. And then on the second blank, my insides are going to now partner. So I've got an H+1 here, and I have an OH -1 here. So I'm going to put on the right-hand side H+, and the OH-. When I crisscross reduce, I wind up with HOH, which is fine if you want to write it like that for now. You could also write it as H2O. So the second blank is going to be H2O. Now, it doesn't really matter for these 2 examples. It doesn't matter if you have your compounds in the opposite blanks. So if you had water in this first blank and magnesium sulfate in the second blank, that would be equally correct. Same is true for the top example. If I have NaCl on top or in the first blank, it would be fine. If I had Al2SO43 in the second blank, it would also be fine. What matters is that you partner the positive with the negative ions and that the positive always goes in front. All right, so that is 2 or 3 examples of double replacement. The next that we need to look at are single replacement. And there are 2 types of single replacement. Number 1 is called a metal replacement. Sometimes you'll hear it called or referred to as cation replacement. When I look at this example at the bottom, I have zinc and hydrogen sulfide. And I know that this is a single replacement because I have a single element and an ionic compound. And what happens is my single element is looking to replace one of the elements in the compound. And it's going to have to replace the element that it is most similar to. So when I look up zinc on my periodic table, I find that zinc is a metal, and as such has a 2+ charge. Okay, zinc is a 2+ charge. When I look up hydrogen and sulfide, hydrogen has a +1 and sulfide has a 2-. So because we are replacing an element, we have to replace or switch out the 2 that are most similar. Because zinc has a positive charge and hydrogen has a positive charge, they will trade places. So hydrogen, you can see here, got kicked out, and zinc has gone into the compound. So they traded places, right? This is written as H2 because it is one of the Brinkelhoff 7. Zinc sulfide is written as ZnS because it was a +2 and a -2. All right, we do have several examples of these, so be patient and get this example down. The other thing that you will notice I have on the slide are a list, or is a list, of different metals. This is called the reactivity series. Now, this isn't complete, but it is a really good list of metals and their reactivity. The top of the list are the most reactive, and the bottom of the list are the least reactive. When you are doing a single replacement reaction, the least reactive element always winds up alone. So when I look at my zinc and my hydrogen, I want to compare the 2 elements that are most alike by charge. So because I have a +2 and a +1, I compare the 2 pluses. Zinc is here. Zinc is here. And hydrogen is here. Because hydrogen is the least reactive, he is closest to the bottom, because he is the least reactive, he winds up alone. The least is always alone. So let's take a look at a couple of examples. So I've gone ahead and I have circled the lone element in these 3 examples. So you can see here I've got silver reacting with copper sulfate. So the first thing I want to do is figure out who is most like silver. Well, silver is a +1, and when I look at my copper sulfate, okay, I've got copper and I've got sulfate, and when I look at them, I have to figure out which one is more like silver. Copper is a metal, sulfate is not. So copper can either be a +2 or a +1, but it is positive, and sulfate is 2-. So when I look at those and I'm trying to decide who to compare, I compare the 2 that are most alike by charge. Positive charge, positive charge. So when I come over to my activity series, I find my copper is listed here, and my silver is listed right below him. So silver in this case is the least reactive. The least reactive ends up alone. Well, silver's already alone, right? He doesn't have another ion next to him. So since silver is the least reactive and will end up alone, if he's already starting out alone, we say for these that no reaction happens, no RXN, because no reaction will happen. That silver will sit in that copper sulfate solution until the end of time, and no reaction will ever happen. Okay, so that's how comparing them and writing the least reactive element by itself works. Okay, if it's already by itself, no reaction. So for the next example, I've got iron and I've got copper chloride. So I've circled iron as the lone element, and I need to figure out which of my elements in this compound is most like iron. Well, iron can be a 2+ or a 3+, but he's a positive charge. When I look up copper, he's either a +1 or a 2+, and chloride is a -1. So in this case, since iron is positive and copper is positive, those are the two that are going to trade places. Those are the two that we compare. So over on the right, I find iron is located here and copper is located here. So copper is the least reactive, so he is going to end up on his own. So to write that, you simply write Cu. Okay. All metals just wind up all by themselves. And then I have one blank that I need to fill in. So this didn't specify which iron to use, so we're going to use iron 3. I'm going to use iron with a 3 charge. So I've got iron with a 3 charge, and I've got chloride, which is just Cl-. Again, look those up on your periodic table, and I'm going to crisscross my charges, and I'm going to write my final answer in the blank, FeCl3. That would be my final answer. I go back and balance if I wanted to. I would need a 2 in front. I would need a 2 in front. I would need a 3 here and a 3 here. And that would give me 2 irons on each side, 3 copper on each side, and 6 chlorine on each side. For now, you'll simply focus your attention on on completing the reaction, and we'll add in balancing a bit later. For the final example, I want to show you one that can get a little bit tricky. When you are working with replacement reactions, and this only is going to help you on replacement reactions, the one thing I want you to look for is water. When you see water in a replacement reaction, it is very often helpful to write it instead of H2O as HOH. That will help you predict products correctly, and it will help you to balance it. So for this one, I'm going to drag up this HOH on top of the formula for water so that we can look at it as HOH and make it just a little bit easier to work with. So what I'm going to do is I've got sodium circled, so I want to compare sodium, and I want to figure out of these two ions which one it is most similar to. So when I split my ions apart, sodium is a +1. When I look up hydrogen, it is a +1, and hydroxide is a -1. So since sodium and hydrogen are both positive, those are the two we compare. So when I come over here to the right-hand side, I'm going to be looking at sodium, which is located here, and hydrogen, which is way down here. So when I look at it, sodium is up at the top and hydrogen is way down toward the bottom. The least reactive ends up alone. The least is alone. So hydrogen is lower. He is the least reactive. And so I will write hydrogen by himself. Keep in mind that hydrogen is one of our Brinkelhoff 7. So he gets a 2. All of my Brinkelhoff elements, those diatomic elements, get a 2. And then I have to fill in my other blank. I have a sodium with a +1, and I have hydroxide with a -1. When I crisscross and reduce, I wind up with NaOH. And those would be my two products. So that's how you do single replacement with metals. The third type of reaction we're going to look at today is also single replacement, but this is going to have halogens. So this is sometimes called anion replacement. This is AKA anion replacement. Anions are negative, and when the halogens are ions, they are negative. The periodic table, you can see I have it kind of over here on the side. The periodic table is the reactivity. Fluorine is the most reactive. And down here, iodine is the least reactive. And this works exactly the same way as the metals, but instead of replacing metals, we're going to trade out halogens. So on this example at the top, we're going to go through this one, and then I'm going to show you a couple more. So on the top, I've got iodine and I've got bromine. And again, I need to know which ones I'm comparing. So I look up charges. Iodine is a -1, calcium is a 2+, and bromine is a -1. These are all on the back of your periodic table. Now remember, we are going to compare the two that are most alike by charge. I'm going to replace those that are most alike by charge. I've got a -1 and I have a -1. So I come over here and compare. Bromine is right here with a -1. Iodine is down below and is the least reactive. The least reactive ends up alone. So this example actually has no reaction. Because the iodine is least reactive and it's already alone, no reaction happens. Always check that, because if you do, you may get to say no reaction and save yourself some extra work. Now let's do a few that will react. So you see I've got chlorine identified. When I look up chlorine, it has a -1 charge. I look up potassium, it has a +1. And I look up bromide, it has a -1. And remember, I'm comparing the two that are most alike by charge. So chlorine is -1, bromine is -1. I compare them. Chlorine is here and bromine is here. So chlorine is most reactive. So this is most reactive, and down here we have the least. And I have bromine as the least reactive. The least reactive ends up alone. So I'm going to write for one of my answers. I've got 2 blanks to fill in. The first one, bromine, ends up alone. Your Brinkelhoff 7, bromine gets a 2. In case you don't remember, Brinkelhoff, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Anytime those 7 elements are by themselves, they get a 2. So bromine is part of that group. He gets the 2. Then I have to fill in my other blank. I know I've got potassium. I always put the plus first. So I've got potassium and I've got chlorine. Now I don't have a 2 next to chlorine here because he is not alone. He's going to bond with the potassium, and so he's not alone. The only time we write that 2 is if it's all by itself. So I've got a +1 and a -1. The formula for this blank is going to be KCl. When I come down to my third example, I've got NaI and Cl2. I've got a circle around Cl2. Chlorine is a -1 charge. Okay. Sodium is a +1 and iodine is a -1. So again, I'm looking at the two that are most similar by charge. So I want to compare them. Chlorine is here. Iodine is well below. So iodine is the least reactive and will end up alone. So I've got 2 blanks to fill in. My first blank is the iodine. And iodine is part of Brinkelhoff. It's right here, iodine. So it does get the 2. In my other blank, I have Na with a +1, and I have Cl with a -1. Remember, I don't bring this 2 over because it breaks apart. The only time I write Cl2 is when it's by itself, unless I need to crisscross and reduce. So to write my final formula, I crisscross my 1's, and I have NaCl2. Oh dear. NaCl. There is no 2. So you have NaCl as your final product. So now that you have watched a few examples and you have taken your notes, now you'll need out your periodic table, your reaction cheat sheet that has an activity series of metals, and you need to complete your 10 practice problems. Let me know if you have any questions. Thanks. Bye.